So here's the LHC underground, and this is the airport and the tram line coming in. We're here where the Atlas detector is situated, so it's sitting in a cavern that's 100 meters underground beneath this building. Then here are the three other experiments that I told you about earlier, where we have our three other interaction points where collisions take place. Atlas and CMS are two detectors that have similar designs and similar physics goals. And they're multi-purpose detectors that are designed to cover the broadest range of the physics that's produced in these LHC collisions. So, you know, we have a whole menu of things that we're interested in seeing produced in these collisions, and Atlas and CMS are trying to cover all of them. ALICE is a more specific detector that's looking primarily at the heavy ion collisions inside of the LHC. 3 months out of the year, rather than proton-proton collisions, we have lead ions colliding. So you have, instead of a single proton, on a single proton, you have several protons and neutrons that collide, which gives you a much more dense environment in the collision, and you need a detector that's optimized to observe those collisions. And in this case, sort of the headlining goal of the ALICE experiment is to study a state of matter called the quark-gluon plasma. We talked about quarks and gluons inside of the proton. Quark-gluon plasma is a state of matter that is supposed to have existed just after the Big Bang, and then not after. So when the universe started to cool and expand, it can no longer support this state of matter, which is characterized by quarks and gluons sort of living or existing in a soup rather than confined to particles like protons. LHCb is our fourth experiment, and it's a more specific detector that looks for very rare decays of particles called B mesons. So these are, again, particles with B quarks in them. And in these decays, we might be able to answer the question of why do we observe this matter-antimatter asymmetry in the universe? So we expect that matter and antimatter were produced in equal amounts at the time of the Big Bang, and now we're left with a matter-dominated universe and no more antimatter is left. So LHCb is looking for what triggered this asymmetry in the evolution of the universe. So here's another view of the Atlas detector. It's down in this cavern. There's the LHCb pipe coming right through it here. Here are the main components of the Atlas detector. So we'll start from the inside and work our way out. In this very central region is our inner detector. It's a tracking spectrometer. The tracking spectrometer is mapping the tracks of charged particles that are produced in the collisions. It's made up of 3 different layers. So at the very center, closest to where the interaction takes place, we have a pixel detector made of silicon chips. That's followed by the semiconducting tracker, silicon strips, and then a transition radiation tracker. And on this side of the wall, you can see examples of what those look like. So these are the pixel modules and the silicon strips and the TRT straw tubes over there. In either case, as a charged particle traverses these media, either the silicon chips or the gas inside of the transition radiation tubes, either an electron will be produced or a photon will be produced, depending on which side you're on. Then this electron or photon is translated into a position measurement for the charged particle that was passing by. If we make several of these position measurements with precision timing instrumentation, then you have a track for that charged particle that was going through the detector. The inner detector sits in a magnetic field that's provided by the solenoid magnets. Now, we place the inner detector in a magnetic field so that these charged particles get deflected inside of the field, so their paths are bent. If you remember outside the picture with the collision taking place, some of the paths of those particles seem to go straight out from the interaction point, and some you could see curving inside of the inner detector. Now, those ones that were curving were lower energy particles that are produced in the collision, so they're deflected more by that magnetic field. The ones that go straight out are still being deflected inside of the inner detector, but those are higher energy particles produced in the collision, so they get deflected less. So with this magnetic field, we can make our first measurement of the momentum or the energy of the particle. Also, we can measure its charge this way because a positively charged particle and a negatively charged particle will be deflected in opposite directions. Following the inner detector, we have in gold here the liquid argon calorimeter, the electromagnetic calorimeter. Inside of this calorimeter, you're measuring energies of electrons and photons produced in the collision. So the material will slow down and absorb this energy of the electron or the photon, and we can measure it inside of the calorimeter. Then we have the tile calorimeter. It serves a similar purpose, but it interacts, it's made out of a different material so that it interacts with different types of particles, so we can start to differentiate between particles based on whether or not their energy is deposited into the electromagnetic or the tile calorimeters. Then, sitting outside of that core, we have the muon detectors. Muons are elementary particles that are just like electrons, except they're 200 times more massive than electrons. And it's by virtue of their mass that they don't interact with the calorimeters. And so we build a secondary tracking system to pick up the muons that are otherwise leaving the detector. We want to be able to identify the muons produced in the collision, so we have this whole secondary tracking system that's designed to look at the tracks of the muons as they leave the detector. And just like the inner detector that was measuring tracks of charged particles had a magnetic field from the solenoid magnet, this muon system has a magnetic field from the toroid magnets. So here is one of them, and there's another, so it's an 8-fold symmetric toroidal superconducting magnet that gives the magnetic field to the muon system, and it's actually what the T in ATLAS comes from. So ATLAS stands for a toroidal LHC apparatus, and it's sort of the easiest way to recognize the ATLAS detector is these big magnets here. Here's the beam pipe coming in. This is a real image of the ATLAS detector, so you can see all of this cabling that's going in and reading out from all the different components and sensors on the detector. Oops, sorry. So here's another nice illustration of how we do particle identification inside of the different layers of the detector. We talked about electrons. So you have an electron that leaves a track inside of this inner detector, and then it deposits its energy inside of the liquid argon calorimeter. A photon looks very similar inside of this electromagnetic calorimeter. It deposits its energy in much the same way, producing this shower inside of it. But we can tell the difference between an electron and a photon by looking back into the inner detector, where the electron has left a track and the photon has not because it's a neutral particle. So this is an important illustration of why we have these different layers of the detector. Where two particles look similar in one part, they look very different in another part, so that we can differentiate between them. And here, by analogy, we have the proton and neutron depositing their energy in the hadronic calorimeter, and then you can tell the difference because the neutron doesn't leave a track inside of the inner detector and the proton does. Here's a muon that's produced in the collisions. So it doesn't interact with the material of the calorimeters, but instead we pick up its track as it otherwise leaves the detector. Now we have another particle called neutrinos, which do not interact with any of the material of the detector. They're neutral, so we don't see their tracks in the inner detector. They're very, very light particles, and they don't interact with the material of these calorimeters. So we can't build a part of the detector so that we can observe directly the neutrinos inside of our collisions. But we need to be able to know when they're there because we need to be able to classify correctly each collision that takes place to perform our analyses. So we use the principle of momentum conservation in order to infer when a neutrino is present inside of the collision. So if you have the two proton beams, or the two protons approaching along one single direction, all of the momentum is contained along that direction. And there's none in this perpendicular direction. And if that's true before the collision takes place, it has to be true after the collision takes place in order to conserve that momentum. So you take all of the particles that you reconstruct inside of this inside of the detector, and you measure their momentum, and then you look at that component that was perpendicular to the initial beam direction, and it should add up to 0. If it hasn't, you can infer that you had a particle produced in the collision carrying the momentum off in the opposite direction so as to cancel it out, but that you didn't directly observe inside of the detector. Questions so far?
So that's the only other particle that you could account for?
You're saying where's the Higgs boson?
Yeah.
Okay. So we have a final class of particles that doesn't appear on this map because they are massive, unstable, and they decay inside of this circle, more or less. So we don't get to see their interactions with the detector. Instead, we look for those particles that the unstable particle decays to. An example is the Higgs boson. An example is the heavy W and Z bosons, or a tau lepton, which is an even heavier version of the electron or muon. These are all examples of particles that decay very soon after their production inside of the collisions. The standard model tells us what are the decay modes for these particles. So we know all of the different ways that the Higgs boson can decay, so we can look for those signatures inside of the detector, and we'll get to look at that a little bit more in just a minute. So the LHC computing grid supports all of the data storage and data analysis that takes place for ATLAS and for the other LHC experiments. But at first, so I haven't told you very much about these collisions, how often they take place. So we have bunches of protons inside of our beams. Each bunch has 100 billion protons in it. Then we cross these bunches every 25 nanoseconds, so that we have 40 million bunch crossings per second. And on average, in 2012, that meant about 20 or 30 interactions times 40 million per second. If we were to read out and process all of that in real time and try and save all of the data from all of the detector, very quickly run out of computing resources. So at the detector level, we have something called a trigger that's going to do a real-time selection and filtering of the events or the collisions that take place in the detector that we actually saved to do our analysis with. And so the trigger is different algorithms that are optimized to hopefully select those events that we are interested in analyzing at the end of the day. But it reduces that rate from 40 million per second down to between 200 and 400 per second. Then at tier 0, this is CERN, the data gets first recorded out from the detector, first reconstructions, and then distribution to our tier 1 and tier 2 sites where we have longer term storage and where the analysis actually takes place. And this makes it possible that we can have an international collaboration of people working from around 40 different countries, 3,000 different members of the ATLAS collaboration, all looking at the same data from the detector and all working on the same analyses together. So we have video conference meetings and emails, and basically I can be talking to anyone from all around the world. But then some of us are also based here, so that we can get excited. Here's one of the first collision events in ATLAS, so maybe not as exciting as this one. This is a candidate of a Z boson that decays to 2 electrons, or an electron-positron pair. So Z boson is an example of one of those particles that decays before it gets to the detector. And instead, what we see in this event is the electron and positron emitted in opposite directions. We see their tracks, and then we measure their energy inside of the calorimeter. So that's what you're seeing. You're looking straight down the detector. This is where the particles are produced. These are their tracks. This is the calorimeter. And this is another way that you can map that energy deposit. In this case, we have observed an electron and positron pair, and we can reconstruct a variable called the invariant mass. And the invariant mass for this 2-particle system is 89 GeV, which is very close to the Z boson mass. This is why we suspect that this could be a Z boson that decays to 2 electrons. And that's why also I call it a candidate. In general, we're not interested in saying this is definitely a Z boson that decays to 2 electrons. Instead, we collect data and data and data so that once we have collected enough, we have enough events that look like this, that it's virtually impossible that all of them are not a Z boson, right? So, for example, if you have 2 muons inside of the detector, and we reconstruct this quantity, the invariant mass of the 2 muon system, and then you plot this variable, and you basically count the number of times you see it in each mass range. And what you'll see is you have these resonances or peaks corresponding to the mass of the particles that can decay to this specific system. So Z boson could have decayed to the 2 electrons. It can also decay to 2 muons. And that's what we see here again at that 90 GeV mass mark. And then there's a few other particles that can also produce 2 muons in the detector. So this is how we search for particles that are decaying before we see them inside of the detector.
So you can't actually see the Z boson, you see the components of it, right?
We see what the Z boson decays to.
Decays to. So the actual mass of the Z boson, or the energy of it, that's a theoretical number, the 89 that
No,
you showed
well,
us?
it's theoretical and it's also verified by doing this. This is observing the Z boson. Here's a candidate for a W boson that decays to a muon and neutrino. So we pick up the muon track leaving the detector, and then we have reconstructed missing momentum in the opposite direction. Jets. So here's a picture of what we call pileup, which is the fact that we have all of these interactions taking place at virtually the same time, all entering the detector, and we have to be able to sift through all of this to pick up the tracks of just 2 particles, for example, when you have all of this in the background. So pileup is a huge challenge with the LHC. Heavy ion collisions in the ATLAS detector. So 3 months out of the year, we're producing the heavy ion collisions. We still look at them at the ATLAS detector, but it's pretty clear from these images that the ATLAS detector is not optimized to look at heavy ion collisions because they basically populate the whole detector, and you can't make much out of anything. All right, here is a candidate Higgs boson that decays to 2 Z bosons, which then decay to 2 muons each. So in the detector, we're looking for 4 muons, and then we can reconstruct the invariant mass still and get back to the Higgs boson mass, so that this is a Higgs boson candidate event where we have 4 muons leaving the detector. What's this? Another way that the Higgs boson can decay is to 2 photons. So here's a very clean signal where we just have the 2 energy deposits from the photons with no associated tracks in the inner detector. And here's a summary of the Higgs boson discovery. So when we were first looking for the Higgs boson in the data at the LHC, we didn't know what its mass was. The standard model tells you all of the ways that the Higgs boson can decay. So it can tell you, for example, look for 2 photons in the detector, look for 4 muons in the detector. But when you reconstruct that invariant mass, the standard model doesn't tell you what you're looking for in that quantity. So you have to do a search for all the mass ranges that are possible within the standard model. So you look in all of the different decay modes. So this is an example of the 2 photon production. You have a background hypothesis, which tells you all of the times you can expect to see 2 photons produced in the collisions if there's no Higgs boson. accounted for. And then you collect data, you collect a lot of data, you reconstruct the invariant mass, and what you see is that at some specific mass point, you have an excess in the number of times that 2 photons are produced. And this excess above your background hypothesis of the number of times that 2 photons are produced corresponds to the number of times that a Higgs boson is being produced and then decaying to those 2 photons. Then you do it in all the different channels where the Higgs boson can decay. So this is an example where we have 4 muons in the detector. And here, this is that corresponding peak, and you see it's at the same mass range. So it's about 125 GeV here. So we have a particle that we've observed that's decaying to all of the decay modes that the standard model predicts the Higgs boson to decay to, and it's happening all at a single mass. So it's the same particle that's decaying to these decay modes. Then we make these funny-looking plots that give us an idea of how confident we can be in the signal that we're observing. So this could just be some statistical fluctuation around our background prediction. But once we collect enough data, then we can say with confidence that no, this is a real excess, this is a real particle that's being produced and decaying to these 2 photons or to these 4 muons. So that's how the Higgs boson was discovered, and it was announced in July of 2012. More people are excited. And we're shut down for 2 years. So performance and maintenance for all of the detectors and the LHC machine in total. So that's why we don't have people sitting in this room. In general, if we were in a data taking period, then you would have each one of these seats populated by some member of the Atlas collaboration. So in general, every person who works on the Atlas experiment is responsible for doing things like taking shifts or doing things related to the performance of the detector so that we are providing data for everyone's analysis. This room is broken up into different sections that correspond to different components of the detector. So you might become an expert in the calorimeter system or the trigger system or one specific part of the detector so that you can then take shifts monitoring the operation as we're taking data. So there's someone sitting in one of these seats for 24 hours a day, 7 days a week. And that's also when the machine is turned on, when the detectors are on, we run stable beams for between 10 and 20 hours, but then when we're not running stable beams, we're preparing for the next stable beam. So it's a really continuous data taking operation throughout the year as we're running. These would usually have some summary information about the performance or the running of the detector and the LHC, but right now they're just feeds down into the Atlas cavern. So you're seeing little corners of the detector, or just a hallway in that case. I don't know if I guess this is the best one where you can see that inner barrel of the detector and the toroid magnets that you can sort of make out right there. Yeah, that's the control room. Are there questions?
So the people in this room are just looking at the data, or do they actually can change things?
No. Well, okay. In emergency situations, things get changed. And you're just looking at the data. So you're accumulating data, and you're looking at sort of a snapshot of it. You're not looking at all of the data. And each group, each subsystem for the detector has a whole team of people that are responsible for it. And we have automated algorithms that look at the data, but then you have someone who's then monitoring those systems as the data is being taken. So usually you could, for example, notice that there's a hot cell in the calorimeter, and there's not much you're going to do about that in real time. You're just going to flag it in that case. Or something that that's really crucial in the time of data taking for the people sitting in the control room is things like trigger rates. if you start accepting too many events at the trigger level, you need to adjust your trigger algorithm so that we're not saving as many events. And that is something that you can change in real time.